So my voice has slightly improved. We'll see how well it does today. I thought we would, let me see, where were we? We got to this idea of phasor differentiation and integration. I think that's when we kind of ran out of time. And but basically, you know, I don't know. So I know you were kind of expecting a test today, and here we are having a lecture. I hope it's okay, but I thought it'd be good to kind of follow up with the lab because we kind of went through some of that fast, kind of get these things anchored. And then tomorrow we can do a practice session, I think, in homework 12. Or if you have any extra questions on the test, you can bring those in too. So we'll do the test on Friday, and everything should go smoothly after that. So I don't have the markups, although I can get them pretty easily. Let's see, they are here. And you know, we developed the notion of a complex number representing a sine wave, and this is sort of the crux of the matter is we want to sort of hijack the complex number representation because it's a great way of encoding two quantities into a single entity. And in the case of sinusoids, they have two quantities. They've got a magnitude and a phase, and it represents that geometrically really, really nicely. And so it allows us to treat sine waves like vectors, which is really pretty cool. And then you can do all kinds of operations with them that make valid sense. And we talked about this idea of a phasor transform. And the phasor transform, I think I wrote on the board, so you all pretty much have that. But in case you're just tuning in, this is important enough probably to repeat the thing that we want to, the thing we'll be doing a lot of in the next week or so, these phasor transforms. So we take a sine wave, which is some magnitude cosine of omega t plus phi, and we can transform that into the phasor domain as a polar form complex number. And well, actually, yeah, we work in that domain, and we really, V of t is the real part of that. That's kind of what this is actually saying. But you do the transform, and you do everything transformed in the phasor domain. You solve, and for something else. Oh, thank you. For another quantity, and that becomes another complex value, quantity, or whatever, and then you can transform that back into the time domain, whatever this qm of t or q of t is. Actually, I don't really mean q, but it's like current or voltage or whatever. I'll call it x, like we did in that other slide, some x quantity, and then that x of t would be xm cosine of omega t plus now theta. So it's easier to do the work in the phasor domain. I should probably, generally what we do is we go this way to solve the problem, and then come back and get it back in the time domain. So this is the forward phasor transform, and this would be the inverse phasor transform going back into the time domain. And you can use this in a lot of things. You can use it for differentiation and integration. And I think we developed that, right? So we did this slide. We kind of did this slide, right? Did we get through that one? I can't remember. They were kind of interrupting a lot. We did differentiation, but did we do integration? So yeah, so to kind of summarize, basically, if v of t is some of Vm cosine of t plus phi, that becomes v bar, which is the angle of phi, and cutting to the chase, dv dt, which is we did a few steps to get that back into a cosine with all that 90-degree phase shift. We kind of got stumped on that. I think everyone's okay with that now. And that's the same thing as W Vm with an angle of phi plus 90 degrees. And we also saw how a 90-degree phase shift is just taking a J out. So that's probably hard to read here, right? It's W omega Vm. And so that's going to equal J omega Vm with an angle of phi. So that's the derivative of a sine wave. And then the integral of a sine wave is the integral of a cosine is 1 over omega of some Vm sine of omega t plus phi plus some constant and just kind of ignoring the constant. I think we're just sort of going to throw that out. It's 1 over omega Vm cosine of omega t plus phi minus 90 degrees. Because in this case it's a plus sign, whereas before it was a minus sign. And that's going to equal in the phasor domain, so we can take that, this is sort of a bit of you can take out that 90 degrees and call that minus J. And that becomes minus J over omega Vm cosine of omega t plus phi. And so that is going to be in the phasor domain. What that amounts to is basically essentially our phasor. If our phasor is Vm angle phi, and then the integral is going to be V bar over J omega. So the two operators, the thing to kind of note is, taking the derivative of a sine wave in the phasor domain or in the time domain is kind of like taking J omega in the phasor domain, and integral in the time domain is kind of like taking 1 over J omega in the phasor domain. And you did Laplace transforms already, right? In the Laplace domain, it's the same thing, right? It's S. The derivative the derivative operator in Laplace domain is multiplied by S, right? And integration is multiplied by 1 over S. And right, they went over that, right? Did they do that yet? In differential equations? Yeah. Well, did they show you how differentiation in the Laplace domain is like multiplying by S? Did they do that? Oh, yeah. In the time domain, it's like multiplying by S in the Laplace domain, right? Yeah, there's that. And then integration is 1 over s times the function in the Laplace domain, right? Yeah, I mean, I kind of thought there's usually a table of these things, and they usually show you this. No integration here. Here we go. Whoops. These properties, right? So differentiation is like s times the function minus initial condition, and then integration is 1 over s times the function. And you can think of actually the phasor domain as kind of like the Laplace domain, where you're restricting s to be on the j omega axis. So you're only dealing with sine waves, in other words, whereas the Laplace domain is kind of a broader class of functions that you can work with. The phasor domain only works with sine waves. But it's less baggage, the Laplace domain kind of comes with a bunch of other stuff, which is kind of confusing. So phasors are kind of like training wheels for Laplace transforms. Really simple. So yeah, so you can use this to solve integral differential equations, provided they have just cosine, sinusoidal excitation. And so that's you could take everything since the derivative is j omega, and integration is 1 over j omega. You could take a differential equation or integral differential equation and transform it into the phasor domain. I go plus 2 for I. In the phasor domain, that's going to be I bar, and then the integral of 8I dt is going to be 8 times the phasor I divided by where's the J2? I'm confused. We're not going to do this much, but I don't know why there's a J. It should just be, because omega is, because omega is 2, right? Okay, so this means omega equals 2 radians per second. So it's j omega, J2, which that's, you can circle this thing and just put j omega there. And minus 3, again, J2 I bar, that's also j omega. And then it's going to equal 50 with an angle of 75 degrees. Yep. No, it's J2, j omega. J times omega. Omega is 2 because of the sine wave having a frequency of 2. So it's J times 2. And so then you can just solve this thing, for phasor I. It's going to be, 4 plus 4 over j minus j6 is going to equal 50 angle 75 degrees. And then phasor I is just going to equal, 50 angle 75 divided by, yeah, well, you can turn 4 over j into, if you multiply 4 over j by j over j, you're going to get minus 4j, right? So minus 4j minus 6j is going to be 10j. So this will just be on the bottom 4 minus j10. And so you're just working with complex numbers now. This is the beauty of it. And square root of 4 squared plus 10 squared is the magnitude, turning this thing from complex to polar, right? With an angle of the arctangent of minus 10 over 4 of the imaginary over the real part is the angle, right? And so that's going to be 50 angle 75 over root 116 angle minus 68 degrees. You're dividing those, so you you 75 minus negative 68 is a phase angle of 143, and the magnitude is 4.64. And back into the time domain, that tells you that I of t is 4.64 cosine of 2t plus 143 degrees. And that would have saved us a whole lot of trouble than if we had to do it using the regular kind of differential equations techniques, like, proposing I as some cosine of it, and then finding boundary conditions and all that stuff. It's just really direct. So it's a nifty little thing, but in differential equations, you would just do this using the Laplace transform instead of Phasor transform. It's more general, but still, if you're just using cosine, sinusoidal excitation, it's pretty convenient. And that leads us to this notion of complex impedance. We kind of talked about that in the lab. That Ohm's law says resistance is V over I. This is what Ohm's law says. Well, in the with phasors, we're going to say phasor Ohm law, right? Phasors of Ohm, I don't know. In the phasor domain, we're going to call it Z. It's a complex number, and that's going to equal V phasor over I. So you can take a component and measure its phasor voltage, its phasor current, and divide those two, and that gives you the equivalent of resistance in the phasor domain. So, in resistors, we say, well, VR is going to equal R times the current through the resistor IR. And if IR of t is some IM cosine of omega t plus theta, and VR of t is going to be R times IM with the same phase angle. This is the time domain. This is the phasor domain. And what that says is, if IR is some IM angle theta, then VR is going to equal R times IM angle theta. And so this thing called ZR is going to equal just VR over IR, which is going to equal R. So ZR, you can think of it as a complex number, but it doesn't have any imaginary part. It's just R with an angle of 0 degrees. That's all. That's just resistors. Yeah, David?
What is IM?
IM is the magnitude of the current, of the sine wave. It's the magnitude of the sine wave that the current is. So in other words, if you take a resistor and you hit it with a sinusoid with a magnitude of IM, frequency of omega and an angle of theta relative to t, to time 0. So you'll get, pictorially, let's see. I'm going to draw this extra page here. Kind of familiar with that Ohm's law curve, right? So basically, this will extend negatively as well. And if you're hitting it with a sine wave that's like going like that, you can map this to a voltage, right? So when you're here, you're going to be here. When you're here, you're going to be here. So that can turn into a voltage that kind of does something very similar, like that, right? So this the magnitude of this is Im. It's the amplitude of the sine wave, and and omega and phi are relative to radians per second, and the phi is relative to t0 where you're at t0. Does that make sense? So I've been doing expectorants. I've been doing lemon tea with honey. It's very persistent. So that's just saying what we already kind of know. With inductors, it's different because now we have that differential relationship, which gives us a j omega in the so IL of t, if you hit an inductor with a sinusoidal current, Im cosine of omega t plus beta, well, we know if we want to find the inductor voltage, that's going to be the derivative times L of the current. That's basically Ohm's law for inductors in the time domain. But because the derivative is like multiplying a phasor by j omega, then VL, phasor VL is going to equal L times j omega times phasor I. And since ZL equals VL over IL, they're all complex numbers, that's going to equal j omega L. So the impedance, you can look at it as, j omega L, or you can look at it as omega L with a phase shift of 90 degrees. That's what that j is. Which, that 90-degree phase shift explains why, when you take the derivative of a sine wave, you get a cosine, right? That's a 90-degree phase shift. So that's what we're representing with the j. The j is just saying you're shifting the phase by 90 degrees. And for capacitors, same idea. In this case, IC equals C dV C dt, and this gives us, in the phasor domain, this gives us IC, with the same reasoning, is going to equal C times J omega VC, but the impedance is the ratio of voltage to current. So that's going to equal 1 over j omega c. which also equals, if you like the j on top, it's minus j over omega c. And ZC in polar form is just 1 over omega c with an angle of minus 90 degrees. Those should all be C's for the capacitor. Whatever voltage you're hitting the capacitor with, VC, it's a phasor voltage. So just like, you know, yeah, if you're talking about in parallel, I mean, yeah, if you set up a specific circuit, yeah. But we're just talking about, you know, so basically if VC is, you know, Vm cosine of omega t plus beta, right? Turn it here, what does it? And my sweater. So phasor VC is just Vm angle theta again. It's just a sine wave. So yeah, Ohm's law, you know, just summarizing again, Ohm's law says that phasor V equals Z times phasor I. And then this is something we can use to solve our circuits. Actually, yeah, we are going to look at a parallel circuit, yep, in the next slide. And this will sort of explain it all too. So with a parallel RLC circuit, you're all getting the same voltage. If we're hitting it with a sine wave, V of t, with some Vm amplitude cosine of omega t plus theta. In the phasor domain, that means we've got V bar equals Vm angle theta degrees. And we want to find, say, IR or IL or IC. So the impedance of the resistor is R. The impedance of the inductor is J omega L. And the impedance of the capacitor is minus J over omega C. And so we can therefore find all those things together. And so in the phasor domain, you know, IR is going to be V over ZR, so that's going to just be Vm over R with an angle of theta, because V had an angle of theta. It's the same phase angle as V. And IL is going to equal V over the inductance impedance ZL. And that's going to be Vm angle theta over J omega L. And it's convenient to think of that as an omega L with an angle of 90 degrees in the denominator, right? So that means when you pull that up, it becomes negative 90 degrees, right? So that equals Vm over omega L with an angle of theta minus 90 degrees. finally, IC equals V over ZC. And that equals Vm angle theta over 1 over omega C with an angle of minus 90 degrees. So that's going to give us omega C Vm with an angle of theta plus 90 degrees.
Why did we call theta 0 for IVAR?
We didn't call theta 0 for IVAR because theta is embedded in our voltage.
Oh,
Yeah, our voltage has some arbitrary phase angle. And again, that means that t equals 0 is just starting off with cosine of theta, Vm cosine of whatever theta is. And then it just starts off from there. So it's got an arbitrary starting point. And what that says in the phasor domain is, you've got your imaginary axis and your real axis. And if your voltage is sitting here at some V, which has some angle theta, and has a magnitude of Vm, the phasor for the capacitor current, well, the phasor for IR is going to be aligned perfectly with V. Because the resistor is going to track the phase. It doesn't have any phase shift in it. It just tracks the voltage instantaneously. Whatever V is, I is going to just be 1 over R times that. And but the capacitor is going to be kind of off here on the left at a 90-degree angle right here. That's a 90-degree angle for IC, scaled, of course, by the frequency and the capacitance. And the inductor is going to be down here, like some kind of IL. IL is going to be over here with a negative. It's it's 90 degrees 90 degrees behind. And in the time domain, sinusoidally, if you take the projections of these things, you'll get the sine waves where, if you just kind of, I don't know if you can fit this in here. It's a room line. In the time domain, this isn't really time domain. That's still a phasor. But if your voltage was something like this, your inductor, so the voltage, maybe if this is V, it's rising, right? The inductor is going to catch up to that 90 degrees later. So the inductor is going to be 90 degrees behind that. It's going to be something like the distance of, a quarter of a period, right? So it's going to be something like here. It's going to kick in, and it'll do something like this. So this is this first one is like V and IR. This one is going to be IL, and IC is going to be leading it. So it would have peaked a little before. It would have done what it's doing a little before. It would be like rising up over here. It's really hard to draw these things. That's why I don't. IC is going to be there. So they all sort of are lining up, but they're shifted with respect to each other. So they're peaking and dropping 90 degrees out of phase with each other. Unless it's the capacitor and the inductor are going to be 180 degrees out of phase. So that's kind of what that's all about. There's also, have you heard this term, inductor Eli the Iceman? Did they go over that in physics? ELI, so yeah, voltage leads the inductance for, and voltage leads current for the inductor, and current leads voltage for the capacitor. So you can squeeze that in somewhere, for R, IR and VR are in phase. Their phases line up perfectly. For L, IL lags the voltage by 90 degrees. And for C, the current leads the voltage by 90 degrees. So this is Eli. This is ice. But that's not the in general thing. The in general part is that in the general sense, a general impedance could have both a actual resistance plus some imaginary part, which we're going to call the reactance. The units are still going to be considered ohms, but now they're complex ohms. And R is the resistance as usual. And X is what we call a new term called the reactance. And if X is greater than 0, that means it is a inductive. If X is less than 0, that means it is a capacitive load. And it looks like an inductor, it looks like a capacitor. And then we have these other things. Oops, I ran out of room here. The element admittance is so this is our thing called impedance. And then admittance is like conductance is to resistance. Admittance is, I'm gonna erase some of this because it's kind of admittance is symbolized by Y, which is 1 over the impedance. It's reciprocal. And the units of that are in Siemens, like or mo's, like conductances. And you can also write Y as G plus J times B, and G is the conductance, and B is the susceptance. There's just so many of these terms, it's kind of hard to keep track of them. And it's the opposite, so if B is greater than 0, that means it is capacitive. And less than 0 means it's inductive. This is all just sort of a little trivia stuff. It's not that hugely important. But in general, once again, these are the important things. ZR equals R. ZL equals J omega L. And ZC equals minus J over omega C. And YR equals 1 over R, which is G. And YL is going to be minus J over omega L. And YC is going to be J omega C. So those are good to know, and those we'll be using kind of going forward. So we got to get through this these last 2 slides. They're really pretty fast, or 3 slides. Network reduction, basically inductance, or I'm sorry, impedances in series. Guess what? It's just like resistors, they add. And in parallel, you do a lot of this stuff. And it's over Z1. The reciprocal of the sum of the reciprocals. So that's all the same, you know, so Z's behave like R's. Y behaves like G. And then finally, the basic procedure of solving these is, you know, for a circuit, like we're going to look at in the next final example, when you get a circuit like this, and we looked at one of these yesterday, transform the sinusoidal time function to phasor, convert all the elements to complex impedances, and then apply network reduction or other circuit principles, just like we did for DC circuits, to determine the response in phasor form, and then transfer the results into a time function. So here's the problem, and we're asked to find VO of t and the current in the resistor. So we got to draw the circuit in the phasor domain first. And, you know, every time we draw the circuit, we're just allowing ourselves to look at this with DC techniques. You know, yeah, we got a sinusoid here. This is our source. This is our VM, and you know, this is our theta, and this is our omega. So we've got a 60 ohm, and we got a capacitor here, and we've got a inductor. Our phasor of our input signal is going to be 20 angle minus 15. You know, our ZR is the same as R. Our ZC is going to be minus J over omega C, which is going to be minus J over 4 times 10 millifarads. That's you know, 10 times 10 to the minus 3. So that's going to be minus J25. So you just have an impedance of minus J25 there. And ZL, which is J omega L, is just going to be J times 4 times 5. It's going to be J20. So I put our J20 here, and we're going to find, we want to find phasor VO. And we also need to find phasor IR. Now, if this was a DC circuit, you would probably realize that you could combine these. If these were resistors, you could combine them pretty easily. Oops. So like these are in parallel, and VO is the voltage across that parallel combination. So you would take the parallel form of that, and then you have a voltage divider, so you can use that formula to find VO. And that's what you would do now, except now they're complex numbers, so it's a little bit more of a pain. So we have to find ZC parallel with ZL, and that's going to equal minus J25 times J20 over minus J25 plus J20. You can see why you want to have a good calculator or, you know, access to FreeMat when you're doing these things. And that equals J100. So you could also find the equivalent impedance of the whole thing. And that's going to be ZR plus 60. I'm sorry, ZR, which is the resistor, plus J100. And yeah, you know, I think FreeMat likes you to say 100J. But the textbook, you're going to see it, it's often going to say J100. Yeah, it starts with a J. Yep. Yeah, I was just thinking I should probably remind you of that. So when you take the reciprocal, so 100 over minus J, you want to get the J out of the denominator. So you multiply times J over J. And J times J is minus 1. Minus 1 times minus 1 is plus 1, so that's just equal to 100J. So the equivalent is ZR plus J100, which is going to be 60 plus J100. And we just got like 4 more lines to finish this thing up. So IR is going to equal VS over Z equivalent. So that's going to be our source voltage, which is 20 angle 15 degrees, minus 15 degrees, sorry, divided by 60 plus J100. And factoring out a 10, you could say that's 2 angle minus 15 degrees over the square root of 6 squared plus 10 squared, angle, running out of room. I hate this. It's really, it's too bad, you know, the screen shrinks when I project it on this projector. That's the problem. So that equals, I'll do it down here. Sorry. It's this with an angle of, and I'm going to just draw an arrow, the arctangent of 10 over 6. So IR is going to equal 2 angle negative 15 over 11.66 angle 59 degrees, which is going to equal 0.172 with an angle of minus 74 degrees. So that's phasor IR, and then V0 is just going to be that times the equivalent. So it's going to be J100, the total equivalent of those two combined impedances, J100 times IR. It's minus 15 minus 59. When you're dividing, yeah, you divide the magnitudes and you subtract. It's the numerator angle minus the denominator angle. Yeah. It's all stuff we did yesterday. It's still kind of new, so you're going to get really used to this. I imagine, I don't know if it helped to have the lab first before the lecture. If this makes a little more sense or maybe not. It's still pretty mysterious until you do it a few times. Probably until tomorrow. We'll do some problems tomorrow and we'll get a sense of it. So V0 is J100 IR, which is going to be 22.3 angle minus 42.5 degrees. Now, before you walk out of here, though, you got to finish. You have one more slide added. So you take that back into the time domain, right? Your IR is going to turn into, well, your VO of t is going to equal 22.3 cosine of 4t minus 42.5 degrees volts, and your IR of t is going to equal 0.172 cosine of 4t minus 74 degrees. So we did all that to get those two values for the output voltage and the current through the resistor as a function of time by going into the phasor domain and then going back when we're all finished. Yep. V naught equals J100 times IR because the equivalence of these two parallel impedances is J100. Yeah, and V naught is the voltage across those. I'm glad you asked. Yeah, I was thinking the same thing. I know all this stuff, if it just washes over you, it's not very valuable, but that's the basic idea, and we're going to be doing that in class tomorrow, so you at least get it anchored before it all goes away for the test. Luckily, this won't be on the test. No, that's fine.
You want to keep it or? No.
This one I'm just checking off.
Good.
This one?
Yeah.
Mm-hmm. Yeah, that's just the current. Yeah, cool. We learned phasors. Yeah, this is the.
That sounds really cool.
Yeah, it's a technique for analyzing AC circuits.